Yep. Right. Yeah. Okay, so last week we discussed the diagonalization, right? So scalar matrix A, n by n matrix A is said to be the diagonalizable if matrix A is similar to the diagonal matrix, that is A is equal to T, D, P inverse. So for some inverted matrix P and some diagonal matrix D. And matrix n by n matrix A is diagonalizable if and only A has n linearly independent eigenvectors. So in fact, A is going to be PD, P inverse, PD, P inverse. So this kind of factorization is called the diagonalization or the eigenvalue decomposition we discussed so far. So if the eigenvectors and eigenvalues of matrix A, it looks like this. Our matrix A can be PD, P inverse, P consisting of the eigenvectors as a column vectors, and D consisting of the eigenvalues on the diagonal term. Yeah, so it was a proof. Yeah, so we discussed how to diagonalize arbitrary matrix A as a PDP inverse. So here, so first of all, we have to know that we have to find the eigenvalues, and we will move to the eigenvector computation and build the matrix P and D. And it's going to the PDP inverse, where P is going to look like this, and P is like this, D is like this. And today, we will see one more theorem, and we will move to the singular value decomposition. Okay. So here's one more theorem. On n by n matrix with the n distinct eigenvalues is diagonalizable. It's diagonalizable. Again, if matrix A has n distinct eigenvalues, then it is diagonalizable. This is one more theorem. The proof of this theorem is very, very simple. Let V1, V2, Vn be the eigenvectors corresponding to the n distinct eigenvalues of matrix A. Then, first of all, V1, V2, Vn is linearly independent. So, independent. Hence, matrix A is diagonalizable by the diagonalization theorem. By the diagonalization theorem we discussed last week. So, we discussed this theorem in chapter 5.1. 그렇죠? Eigenvectors are linearly dependent. 그렇죠? If the eigenvalues are distinct, right? So n by n matrix with n distinct eigenvalues is diagonalizable. This is one more theorem. One more thing is that if let matrix A be an n by n matrix whose distinct eigenvalues are lambda 1, lambda 2, and lambda p. In this case, p is smaller than n. 그렇죠? Smaller than n. Then there are several kinds of properties. Okay. First of all, p is smaller than n. Then if for k is greater than equals to 1 or smaller than equals to p, the dimension of the eigenspace for the lambda k is less than or equals to the multiplicity of the eigenvalues of the lambda k. Eigenvalues of lambda k. So what does it mean? So when we think characteristic equation, so this is kind of lambda minus lambda k to the alpha blah 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 blah, right? So in this case, this alpha is called the multiplicity, 그렇죠? Which is alpha for the eigenvalue lambda k. In this case, dimension of the eigenspace for the lambda k is less than or the equals to the multiplicity. If alpha is equal to 2, the eigenspace for the lambda k is the dimension of the eigenspace for the lambda k is less than or equals to the 2, because the alpha was 2. This is the first statement. The second statement is that matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n, and this happens if and only if characteristic polynomial vectors completely into the linear vectors, and dimension of the eigenspace for the each lambda k equals to the multiplicity of the lambda k. So what does it mean? Characteristic polynomial vectors, the linear vectors, and it means that when we find the eigen characteristic polynomial, it should be looks like lambda minus lambda 1 over let's say 1, for example, or lambda minus lambda 2 times 3 blah blah blah. So it should be linear vector. It should be decomposed as a linear vectors, and dimension of the eigenspace for each lambda k equals to multiplicity of lambda k, which means eigenspace for the lambda 1 should be 1, and eigenspace for the lambda 2 should be 2. Looks like this, blah blah blah. Then in this case, matrix A is diagonalizable. So this is kind of constraint to make a matrix A is diagonalizable. One more thing is that matrix A is diagonalizable, and PK is the basis for the eigenspace corresponding to lambda k for each k. The total collection of the vectors in the set P1, PP forms an eigenvector basis for the Rn. Again, if matrix A is diagonalizable and let's say there are lambda k eigenvalues, then let's say pk is the basis for the eigenspace, then total collection of the vectors in the set P1, P2, Pp forms the eigenvector basis for the lambda n. This is the properties for the eigenvectors. This kind of theorem can be applied to the matrix whose eigenvalues are not distinct. Whose eigenvectors are not distinct. If matrix A has n distinct eigenvalues, it is just diagonalizable. But if not, we have to consider, we have to follow up this kind of further constraint. This is properties. And yeah, let me show you a very simple example. Let's diagonalize the following matrix if possible. So first of all, our input matrix A is a triangle matrix. Triangular matrix. So first of all, we have to find the eigenvalues for this matrix A, right? So how can I find eigenvalues? So we have to consider the determinant of A minus lambda I, right? So because this is the triangle form, our determinant of this matrix is going to be 5 minus lambda, 5 minus lambda, and negative 3 minus lambda, negative 3 minus lambda. In this semester we did not discuss how to compute this one, but we will just use the determinant computation way to find out this characteristic polynomial. And in this case, it's going to be the lambda minus 5 to the 2, lambda plus 3 to the 2 is equal to 0. So our lambda is going to be our eigenvalues is going to be 5 over negative 3. 5 over negative 3. Then we can find out corresponding eigenvectors for the lambda is equal to 5 or lambda is equal to negative 3. Right? Again, since matrix A is a triangular matrix, eigenvalues are 5 and negative 3, each with multiplicity 2. 그렇죠? here and here, 그쵸? 2. We find the basis for each eigenspace, right? Each eigenspace. How? First of all, if the lambda is equal to 5, we can find the solution for the matrix equation A minus 5 identity matrix times vector x is equal to 0, x is equal to 0. Because we already know matrix A, we can easily find out this matrix. So this matrix, there's 0, 0, 1, negative 1, 0, 0, 4, negative 2, 0, 0, negative 8, 0, 0, 0, 0, negative 8. Then you can easily find the null space of this matrix A. 그렇죠? Null space A. Then basis for this null space, I mean the solution for this homogeneous system is going to be V1 is like that, V2 is like that. Please try to solve yourself. 그렇죠? This is just finding null space. You can easily do that. Similarly, lambda is equal to negative 3. Then your eigenvectors is going to be in eigenspace such that A plus 3 I x is equal to 0 vector, where this vector is going to be A 0, 1, negative 1, 0, A 4, negative 2, 0, 0, 0, 0, 0, 0, 0, 0. Then x is equal to 0. Then solution. The basis for this eigenspace is going to be V3 and V4, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So please try to solve yourself. So first of all, when it's have V1, V2, and V3, and V4, they are linearly independent. So matrix P is invertible. Matrix P is invertible because the V1, V2, V3, and V3 are linearly independent. 그렇죠? So invertible. So our matrix A is going to be P, D, P inverse, where P is like this, consisting of eigenvectors V1, V2, V3, V4, and T consisting of the eigenvalues 5, 5, negative 3, negative 3. So we can factorize matrix A as a P, D, P inverse, P, D, P inverse. This is one of the example to diagonalize your matrix. All right, so this is end of chapter 5.3. In this chapter we discuss how to diagonalize your own matrix A. Sure. Question? No? Okay, so today we'll move to our last lecture note. Lecture to 13, singular value decomposition. In fact, the singular value decomposition is kind of extension of the lecture to 12, eigenvalue, eigenvectors. Okay, so this is singular value decomposition. So this is chapter 7.1, diagonalization of the symmetric matrix. 그렇죠? So first of all, in chapter 5.3, we discussed how to diagonalize your matrix, but here, chapter 7.1, we will talk about the specific diagonalization of the symmetric matrix. Okay, like this. What is symmetric matrix? We already talked about symmetric matrix, right? So symmetric matrix is a matrix A, such that A transpose equals to matrix A, 그렇죠? Original matrix A. Then such a matrix is necessary square, 그렇죠? AT is equal to A, so matrix A should be square. Its main diagonal entries are arbitrary, but each other entries occurs in pairs on the opposite side of the main diagonal. For example, let's say our matrix A is 0, 5, 7 on main diagonal, but off-diagonal term should be symmetric across the main diagonal. For example, -1, 0, 8. Then this one should be -1, 0, 8. Or in this case, AT, it's going to be 0, -1, 0, -1, 5, 8, 0, 8, 7. Right? So this is kind of symmetric matrix. So if the matrix A is symmetric, it's not a n by n matrix anymore. It's not just n by n matrix. If matrix A is symmetric matrix, then two eigenvectors from different eigenspace are also known. This is additional properties of the eigenvectors. If matrix A is symmetric, any two eigenvectors from the different eigenspace are also know each other. This is theorem 1. This is theorem 1. So you can easily prove this one. Let V1 and V2 be eigenvectors that correspond to distinct eigenvalues. Let's say λ1 and λ2, and then λ2. We have to show that V1 inner product V2 is equal to 0. You can easily do that, right? So first of all, let's suppose that λ1 times V1 inner product V2, then it's going to be λ1 V1 transpose V2 by the properties of the inner product, 그렇죠? Like this. Then, because this is eigenvalues and eigenvectors, λ1 V1 is going to be A V1, 그렇죠? This is just the definition. Then A V1 transpose V2, 그렇죠? Then V1 transpose A transpose times V2, 그렇죠? Because this is the transpose of vector or multiplication, vector or matrix. 그렇죠? Then V1 transpose times A V2. 그렇죠? Then V1 transpose times λ2 V2. Because this is eigenvalues and eigenvectors. 그렇죠? Then λ2, because λ2 is a scalar value, λ2 times V1 transpose times V2. Then λ2 V1 in the product of V2. So here we can see λ1 V1 in the product of V2 is equal to λ2 V1 in the product of V2. Hence, if we subtract from left hand side to the right hand side, λ1 minus λ2 times inner product of V1 and V2 is equal to 0, right? So here we just assume λ1 and λ2 is not equal to 0 because we just assume two eigenvalues are different, 그렇죠? So V1, V2 should be 0. Inner product V1 and V2 should be 0. So in other words, two eigenvectors V1 and V2 are orthogonal. So like this. If matrix A is similar, two eigenvectors are orthogonal. This is the new theorem for the symmetric matrix case. Again, please do not focus on the proof. 그쵸? Please try to understand just the meaning of this theorem. 그쵸? 네, 항상 얘기했지만 여러분 챕터 지금 12, 13으로 넘어오면서 렉처 노트 12, 13으로 넘어오면서 정말 많은 theorem들이 나오고 있죠? 아마 이런 것들을 다 기억하려고 그러면 너무너무 어려울 거야. 수업을 특히 열심히 듣는 친구들은 제가 계속 얘기했으니까 벼락치기 하는 친구들은 아마 모를 수도 있는데 꼭 너무 여기 집중하지 말고 이 의미, 매트릭스 A가 시메트릭이면은 아이겐밸류, 다른 아이겐밸류부터 나온 아이겐벡터는 올소원활하다 라고 하는 프로퍼티 잘 이해하고 있으면 돼요. 그렇죠? 이제 그 프로퍼티가 우리의 마지막 어떤 팩토라이제이션을 어떤 포뮬레이션 하는데 쓰이거든요. 그렇기 때문에 이 시어럼들을 잘 이해만 하고 있으면 괜찮을 거예요. 알겠죠? Right. So one more thing is the orthogonal matrix. What is orthogonal matrix? We only talk about this one in lecture 11. 그쵸? lecture 11. Orthogonal matrix is a square inverter matrix U, such that U inverse equals to U transpose. Okay. So for example, such a matrix is consisting of the column vector U1, U2, and UN. So in this kind of orthogonal matrix has orthonormal columns. So each other should be orthonormal. So this is orthogonal matrix. In other words, any square matrix with a orthonormal columns is called orthogonal matrix. orthogonal matrix. This is just definition. orthogonal matrix. If a matrix has orthonormal columns. 기억하죠? orthonormal columns 기억하죠? 각각이 랭스가 1이고 각각 서로가 orthogonal할 때 우리가 orthogonal matrix를 한다 라는 거였고요. Why do we have to know that? To derive orthogonally diagonalizable concept. orthogonally diagonalizable. Okay, so in chapter 5.3, we just talk about diagonalization, 그쵸? diagonalizable, 그쵸? But in chapter 7.1, we will talk about orthogonally diagonalizable. What is it? If n by n matrix A is said to be orthogonally diagonalizable if there are orthogonal matrix P. In other words, if the matrix P is orthogonal matrix, P inverse is equal to P transpose. 그렇죠? And diagonal matrix D. Then we can factorize matrix A as a P, D, P transpose because P transpose equal to P inverse, so it's going to be P, D, P inverse. Then in this case, this kind of factorization is called matrix A is orthogonally diagonalizable or orthogonal diagonalization. This is a specific factorization for the symmetry matrix. So such a diagonalization requires n linear independent and also normal eigenvectors. Okay. Eigenvectors should be linear independent and it should be also normal eigenvectors because we just assume also orthogonal matrix P must be. Then if matrix A is orthogonally diagonalizable, then A transpose is going to be the transpose of P, D, P transpose is going to be the P, D, P transpose, and which is going to be A. So matrix A is symmetric. Matrix A is symmetric. In other words, if matrix A is symmetric, we can find out P, D, P inverse, where D is the eigenvector. D consists of eigenvalues and P is consists of eigenvector that are linear independent and also normal each other. Then we can factorize like this. To summarize, matrix A is orthogonally diagonalizable if and only if matrix A is symmetric matrix. 그래서 한국말로 다시 한번 얘기하면은 무슨 얘기를 하고 싶은 거냐? matrix A가 symmetric하면 matrix A는 orthogonally diagonalizable하다. 원래 diagonalizable가 뭐가 다르냐? 요 P가 orthogonal matrix로 구성되어 있다. 왜 언제가 orthogonal matrix냐? 매트릭스 P가 also normal 벡터들로 구성되어 있던 경우에. 그렇죠? 왜 그러냐? 아이겐벡터가 다를 때는 아이겐벡터들이 올소고널했기 때문에 자연스럽게 시메트릭 매트릭스인 경우는 아이겐벡터들이 올소노멀 컬럼들을 아니죠. 아이겐벡터들을 올소노멀하게 만들 수만 있다면 우리는 이런 올소고널 다이고널라이제이션을 만들 수가 있더라. 시메트릭 매트릭스인 경우에. Theorem 2에서 하고 싶은 얘기죠. question. 자, 우리 이제 여기까지 질문 있을까요? So final reason cover will by chapter 7.1 this chapter and chapter 7.3 the next chapter. 그렇죠? 여기까지 우리 시험 범위 들어가긴 할 건데 질문. 그러니까 우리가 저번 시간에 다이고널라이제이션을 배웠었고 A가 매트릭스 A가 시메트리인 경우는 조금 더 특별하게 다이고널라이제이션 될 수 있는데 올소고널리 다이고널라이제이블 하다. 그러니까 P가 올소고널 매트릭스가 될 수 있다 라고 하는 게 이제 특별한 스페시픽 케이스였죠. 그렇죠? 시메트리인 경우에. question. Let me show you an example because it looks very complicating. So I will just give you very simple example. The question was orthogonally diagonalize the matrix A 3, -2, 4, 6, 4, 2, 3, whose characteristic equation is like this. Characteristic equation means determinant of A minus lambda I equals 0. So it's going to look like this. So first of all, matrix A is symmetric or not? 자, matrix A is symmetric or not? 자, matrix A가 symmetric 할까요, 안 할까요? 지금 이 상태에서. Matrix A is symmetric or non-symmetric? 그쵸? 뭘 해요? Symmetric. 그쵸? Symmetric. 그쵸? Then we can observe it is also only diagonalizable. It's only diagonalizable. And first of all, in this matrix A, our eigenvalues, it's going to be the 7 and -2, where each multiplicity is 2 here, 그쵸? And multiplicity 1 here. Then let's find the eigenvectors. 그쵸? Eigenvectors. 그쵸? First of all, usual calculation produces a basis for the eigenspace. What? When lambda is equal to 7, we're going to find A minus lambda is equal to 7, 그렇죠? A minus 7 I is equal to 0. Then basis for this eigenspace is going to be the V1 and V2, 그렇죠? Please try to derive yourself. I just assume you can do that. I just assume you can do that because we already discussed so many times how to find the basis for the null space. 그렇죠? Similarly, when lambda is equal to -2, it's going to be A minus A plus, 그렇죠? A plus 2 lambda, A plus 2 I equal to 0. Then eigenspace for this one is going to be the V3. -1 or 2, 1. So, first of all, we already know V1 and V2 are linearly independent, 그렇죠? Because they are basis for the eigenspace. So they are linearly independent. But they are not orthogonal. They are not orthogonal. 그렇죠? So what does it mean? In this case, V1 and V2, inner product V1 and V2 are not equal to 0. Not equal to 0. Then let's find out orthogonal basis for the eigenspace for the lambda is equal to 7. So the question is how to make orthogonal basis when V1 is like this, V2 is like this. We already talk about this one in Gram-Schmidt process. 그렇죠? Gram-Schmidt process. First of all, let's fix V1 and let's find the projection of the V2 onto V1. In other words, because here is the V1 and here let's suppose here is V2. To make also gonal basis, let's find out projection of V2 onto V1. 그렇죠? Then we can find out this vector, 그렇죠? Also gonal vector, 그렇죠? Like this. So by the definition, projection of the V2 onto V1, it's going to be the V2 inner product V1 over V1 inner product V1 times V1. This is just the definition, 그렇죠? This is just definition. Then component of V2 orthogonal to V1. This one, 그렇죠? This one, it's going to be V2 minus V2 inner product V1 over V1 inner product V1 times V1. 그렇죠? 그렇죠? Similar to the Gram-Schmidt process. Then G2 is going to be V1 minus V2 minus V2 inner product V1 over V1 inner product V1 times V1. We already know what V2 is, V1 is. 그렇죠? V1 is like this. Then you can easily find out this one, and V1 was 1, 0, 1. Then our new G2 is going to be negative 1 over 4, 1 over 4. Then V1 and G2 is orthogonal set in the eigenspace for lambda is equal to 2. Lambda is equal to 7. 그렇죠? Note that G2 is a linear combination of the eigenvectors V1 and V2. So V2 is in eigenspace, so we can easily say that V1 and V2 is a new basis for this eigenspace for the lambda is equal to 7, and they also know each other. So orthogonal set V1, Z2 is also gonal basis for the eigenspace by the basis theorem. So because the eigenspace is two-dimensional, these two kinds of vectors are also gonal basis, right? Then we want to find out also normal basis. So we just normalize V1 and Z2 to obtain the following also normal basis for the eigenspace for the lambda is equal to 7. So let's just normalize V1 to the U1, G to the U2. Then our new matrix vector U1 and U2 is going to be this one and this one. How to normalize? Just like this. 그렇죠? Original vector U1 over length of the length V1 over length of the V1, and U2 is going to be G1 over length of G2 over length of G2. One more thing is that because the eigenspace for the lambda is equal to negative 2 only has the one vector as a basis, so you can easily find the also normal basis by just normalize just V3, 그쵸? just V3. So it's going to be U3. It's going to look like this. So because the U3 is orthogonal to the other eigenvectors U1 and U2 because they are coming from the different eigenvectors, 그쵸? Coming from the different eigenvalues, 그쵸? Eigenvalues. So we can say that U1, U2, and U3 are also normal set. U1, U2, and U3 are also normal set. Also normal set. Then you can set matrix P consisting of eigenvectors U1, U2, and U3. Then our new vector P is going to be U1, U2, and U3. And matrix T consisting of the eigenvalues 7, 7, negative 2, negative 2. Then we can say that matrix A is orthogonally diagonalizable, or matrix P orthogonally diagonalized matrix A. Then and matrix A is going to be the P, D, P inverse, where P is like this like this. Then we can say that matrix A is orthogonally diagonalizable. Orthogonally diagonalizable. So let me explain in this one in Korean. 자, 이제 우리가 시메트릭 매트릭스인 경우에 우리가 이전에 챕터 5.3절 여기서 lecture 12에서 배웠을 때는 매트릭스 A가 시메트릭이라고는 고려하지 않았어요. 그렇죠? 그냥 P와 D의 P와 D로 다이고널라이제이션 하는 것만 얘기했었는데 특별하게 매트릭스 A가 시메트릭인 경우에는 우리가 앞에 얘기했던 프로퍼티스 때문에 두 개의 아이겐벡터, 그러니까 그 아이겐밸류들의 아이겐벡터들이 그 뭐예요? 올소고널하다라는 걸 알고 있으니까 V1과 V2가 리니어 인디펜던트하고 올소고널하는 게만 만들어내면 어떻게 만들죠? 우리가 아비트리 매트릭스 V1과 V2가 있었을 때는 여기서 이제 우리가 그램 슈미스 프로세스를 통해서 올소고널한 벡터를 만들었었죠. 노멀라이즈하면 그게 바로 올소 노멀이 되는 거였고, 그래서 V1, Z2를 만들어서 U1, U2를 만들어버리면, 그리고 U3를 만들면 이 소개가 이 세 개 올소 노멀 매트릭스가 되는 거고 올소고널 매트릭스가 되는 거고, 그쵸? 이때 우리가 아비트리 매트릭스 A, 즉 시메트릭 매트릭스인 경우는 PD로 PD, P 인버스를 만들 수 있는데 이때 P가 이렇게 구성이 되고 D가 아이겐밸류로 구성이 되도록 만들 수 있고, 이 P는 올소고널 매트릭스라는 아주 특별한 성질을 지니더라 라고 한다는 거죠. 그렇죠? 이 올소고널 매트릭스, P가 올소고널 매트릭스인 게 이제 너무 좋은 프로퍼티들을 뒤에서 보여줄 건데 일단 그렇게 되더라 라는 거죠. 그렇죠? 자, question. 자, 동일학생 질문이 A가 시메트릭하다면 A에 해당하는 P는 also 노멀 해야 되기 때문에 A의 아이겐밸류를 그램 슈미트 과정으로 P를 구성하여 준다. 그램 슈미트 과정은 아이겐 스페이스 안에 있다. 너무너무 좋은 질문이고요, 동일학생. 그램 슈미트 프로세스를 해가지고 같은 아이겐 스페이스상의 벡터, 베이시스 벡터들을 올소고널에 만들어주면 되고요. 다른 아이겐 스페이스에 존재하는, 즉 그림을 그려볼까요? 예를 들어서 우리가 알고 있는 다른 아이겐밸류에서 나온 아이겐 스페이스, 아이겐 벡터들은 올소고널하다고 하는 게 우리가 프로퍼티스에서 봤었죠. 여기서, 그렇죠? 그렇기 때문에 다른 아이겐 벡터들, 그러니까 다른 아이겐 스페이스 나온 다른 아이겐 벡터들 간에는 우리가 따로 그램 슈미트 프로세스 해줄 필요가 없는 거죠. 그렇죠? 그래서 이걸 그림으로 한번 표현해 보면, 우리가 뭐 그림으로 굳이 표현을 해보면, let's say this is the eigen space for lambda is equal to 7. let's say there's another space, eigen space for lambda is equal to -2, then we can say that there is one of the vectors in this eigenspace, let's say U3, and here's another matrix U2, U1 and U2. They are orthogonal to each other, and U1 and U3 are orthogonal, and U2 and U3 are orthogonal because this is the from the theorem. 그렇죠? 이렇게 그림 볼 수 있을 거야. 그렇죠? 너무 좋은 질문이네요. 자, other question. No. Okay. In fact, this theorem is similar related to the spectral theorem, or the set of the eigenvalues of matrix A is sometimes called the spectrum of the matrix A. So we just call this one is a spectral theorem. So eigenvalues, the set of the eigenvalues is sometimes called spectrum of matrix A. Then we will introduce one more theorem, spectrum theorem. The spectrum theorem for the symmetric matrix. Spectral theorem. If A is n by n symmetric matrix, then matrix A has the following properties. First of all, matrix A has n real eigenvalues. Computing multiplicity. It means that, okay. I will show you examples. Here, there is a two eigenvalues, lambda is equal to 2, and lambda is equal to -2, and matrix A was 3 by 3, but lambda is equal to 2, it has multiplicity 2, so we can just say that there exists n as 3 real eigenvalue, 7, 7, -2, 7, 7, -2. So here, n real eigenvalues, counting multiplicity. This is the first property. The second property is that dimension of the eigenspace for each eigenvalues, lambda, dimension of the eigenspace for the each eigenvalue, lambda, equals to multiplicity of the lambda as the root of the characteristic equation. For example, dimension of the eigenspace equals to multiplicity of lambda. So for example, in this case, lambda is 2. Dimension, normality of the lambda is equals 2 is the 2. 그렇죠? There are two vectors as a basis. Why? Because the multiplicity was 2. For lambda is equal to -2, multiplicity was 1. So dimension of this one as just 1. So there's only single vector. 그렇죠? In other words, dimension of the eigenspace equals to multiplicity of the lambda. 그렇죠? 그래서 정리해 보면은 그 캐릭터리스티케이션을 그려왔을 때, 그러니까 계산해 봤을 때 캐릭터리스티케이션의 멀티플리시티까지 고려하면 그 멀티플리시티의 그러니까 지수성이죠. 멀티플리시티가 아이겐스페이스의 디멘전, 즉 베이시스의 개수와 똑같더라. 앞에 예시에서 그냥 볼 수 있죠. 증명은 필요 없이. 그렇죠? 그 다음에 Eigenspaces are mutually orthogonal in the sense that eigenvectors corresponding to the different eigenvalues are orthogonal. We already talked about this one in previous example. 그렇죠? 그렇죠? previous theorem. 그렇죠? 그래서 다른 아이겐밸류로부터 나온 아이겐벡터들은 서로 올수고나 하더라. 하는 properties. A가 올수고나 diagonalizable다. 즉, matrix A is orthogonally diagonalizable. 하다. This is a spectral theorem. Spectral theorem. 그렇죠? 이게 이제 spectral theorem이라고 한다라는 거죠. 그렇죠? So we want to prove this property or theorem, but you can easily check this theorem is true from this previous example. 그렇죠? 정확히 프로퍼티 example이 A가 시메트릭 매트릭스인 경우에 이 프로퍼티스 만족하는 걸 보여주죠. 이렇게 체크를 해보면 되죠. In other words, suppose that matrix A is equals to PD P inverse, where constant matrix P are also known eigenvalues U1, U2, and UN of matrix A, and corresponding eigenvalues lambda 1 and lambda n in diagonal matrix T. Then, because the P is also gonal matrix, so P inverse is equal to PT, 그렇죠? Then your matrix A can be factorized as a P, D, P inverse, where P is like this, T is like this, and P inverse like this. 그렇죠? P inverse like this. Then this kind of factorization or decomposition called spectral decomposition, or this factorization is called Eigen decomposition. Eigenvectors. Again, if matrix A is symmetric, your eigen decomposition can factorize original matrix A as like this. P, D, P inverse. P, D, P inverse. This is the spectral decomposition and eigen decomposition. So, eigen decomposition. Again, this one can be reformulated like lambda 1, U1 from this one. 그렇죠? And lambda 2, U2 and lambda n, UN and times U transpose. 그렇죠? 그 P inverse죠. 그렇죠? Then using the column row expansion of the product, 그렇죠? Just by computing matrix multiplication, it's going to be matrix A. It's going to be lambda 1, U1, U1 transpose, lambda 2, U2, U transpose, UN, lambda n, UN, UN transpose. 그렇죠? Like this. This representation of matrix A is called spectral decomposition. So, first of all, U1 times U1. 그렇죠? First of all, U1 is in n by 1. Then U1 times U1 transpose is going to be the n by n. n by n. n by n. 그렇죠? Then this matrix is also n by n, where original matrix A is also n by n. And this matrix is also n by n. Then it means that you can factorize, or you can represent original n by n matrix A as a sum of the n by n matrix, n kinds of n by n matrix. This is called spectral decomposition or eigenvalue decomposition. This is one of the most important factorization in this semester. So, this is the spectral decomposition. 자, 우리 한 번만 더 설명할게요. 자, 우리가 이제 챕터 12부터 렉처부터 12부터 여기까지 왔는데 왜 계속 열심히 아이겐밸류, 아이겐벡터를 왜 공부를 해왔냐? 요거 하려고 한 거예요. 스펙트럴 디컴포지션이라고 하는 걸 도달하기 위해서 우리 여기까지 온 거야. 너무너무너무 중요한 팩토라이제이션이고 아마 여러분들이 이번 학기에 배워야 되는 가장 중요한 디컴포지션이 바로 이 디컴포지션을 해도 과언이 아닐 정도로 너무나 많이 쓰이고 너무나 중요한, 너무나 의미 있는 팩토라이제이션 중에 하나가 바로 이 spectral decomposition, spectral factorization, or eigenvalue, eigen decomposition 이라고 하는 거예요. 뭐냐? n by n matrix, 매트릭스 A가 시메트릭일 때 n by n matrix는 n개의, 즉 얘가 전체 n개가 있죠? 그렇죠? n개의 n by n matrix의 합으로 이루어져 있다 라고 하는 프로퍼티스예요. 합으로 이루어져 있다 라고 하는 프로퍼티스예요. 근데 어떤 합이냐? 매트릭스 A의 아이겐밸류와 해당하는 아이겐벡터로 만든 n by n 매트릭스들의 서메이션으로 이루어져 있다 라고 하는 게 매트릭스 스펙트럴 팩토라이제이션 이라고 하는 거예요. Why? Why do you have to know that? So this spectral factorization can be used in so many kinds of application or the field. So one of the field is the approximation. For example, okay, so you want to represent your arbitrary matrix A as a new matrix that approximate original matrix A, but more easy to handle. Then in this case, you can represent your matrix A as a sum of this term, 그렇죠? Sum of term in the Eigen spectral decomposition. For example, you can represent your matrix A as a lambda 1 times vector U1 times U1 transpose plus lambda 2 U2 times U2 transpose, something like this. Then in this case, this one is the approximation of matrix A, but it's not a original matrix A, but this matrix is this one, 그쵸? These two terms, 그쵸? The first term can fill new matrix, n by n matrix, then it's going to be the best approximated matrix for the original matrix A. In other words, this term, first term can contain most of information for the matrix A, and the second term contain the information after this first matrix. Then next one has the less important information, blah, blah, blah. So you can use this factorization as the approximated matrix for the original matrix A or the compact representation for the matrix A. 근데 이제 이런 게 어디에 쓰이냐면 이런 거예요. 그러니까 여러분들이 이제 이게 말했지만 이번 학기에 가장 중요한 theorem 중에 하나예요. Spectral factorization. Your matrix A가 symmetry인 경우에 이런 n by n 매트릭스들의 합으로 나타날 수 있는데 너무 많은 곳에 쓰일 수가 있어요. 첫 번째가 이게 각각 다 n by n 매트릭스라고 했죠. 그랬을 때 이제 뒤에서 이제 잠깐 얘기할 건데 이 람다의 값에 따라서 이 매트릭스 A의 중요한 정보들이 순차적으로 담겨 있어요. 무슨 얘기냐? 첫 번째 매트릭스가 가장 정보를 많이 담고 있고 두 번째 매트릭스가 조금 덜 담고 있고 세 번째가 조금 덜 담고 있고 이런 식으로 담고 있어요. 그 말은 뭐냐? 여러분들 매트릭스 A를 조금 더 어프록시메이션 하지만 핸들링하기 쉬운 매트릭스로 표현하고 싶을 때 이 아이겐 벡터들과 아이겐 밸류들로 만들어진 이 상위에 몇 개 텀을 쓰느냐를 가지고 어프록시메이션 할 수가 있다는 거죠. 그렇죠? 그러니까 이거 n개를 다 쓰면 가장 어프록시메이션을 잘하는 거죠. 에러가 0일 테니까. 그렇죠? 근데 상위 몇 개를 쓰면 에러가 있겠지만 매트릭스 A를 가장 잘 표현할 수 있으면서도 이러한 어떤 특별한 케이스, 어떤 뭐예요? 매트릭스 두 개의 벡터들의 곱으로 이루어져 있는 아주 간단한 매트릭스 폼이기 때문에 나중에 얘기하겠지만 핸들링하기 매우 쉬운 특별한 폼을 가지고 있어서 이런 식으로 우리가 어프록시메이션을 할 수가 있다라고 하는 거. 이제 어떤 매트릭스를 어떤 압축한다든지 또는 어떤 어프로시메이티드 솔루션을 찾는다든지 하는데 이제 이러한 아이겐 밸류, 아이겐 디컴포지션 또는 스펙트럴 디컴포지션이 너무너무 많이 쓰이게 될 거예요. 그렇죠? 이제 이렇게 중요한 특성이 있더라라고 하는 거죠. 알겠죠? question? question. So first of all, this one, each matrix, uj times uj transpose, 그렇죠? 이 transpose, n by m transpose, n by m matrix, 이죠? It's called projection matrix in the sense that for each vector x in our space, the vector uj transpose x is also a projection of x onto the space spanned by uj.
没有，
We
我
already
不想
discussed
挂个
this
课，我这手机一直挂着网课。
factorization, 아니죠? 올소말 프로젝션, 그렇죠? 우리가 이 u가 놀수 노멀일 때 그냥 이렇게 쉽게 나타날 수 있다라고 하는 거, 올소말 프로젝션 이렇게 나타날 수 있다고 하는 거, 우리가 already 얘기를 했었어요.
这都是
그렇죠?
家庭妇男。
这是裤子吗？
네, 이런 거다라고 하는 거고. 자, 이게 어떤 의미를 가지냐? So, for example, let's suppose that your matrix A equation A equals B. Well, let's suppose that this matrix has no solution or even have solution. Then let's suppose that
哎呀，我在想我要不要学习？
Eigen
我觉得你
space for the
闹
matrix
钱
A
我学
has
习也
a
不太好，好像
U1, U2, and U3.
浪费。
U3. Then eigenfactorization of the matrix A
有道理。
哎呀，
was lambda 1 U1 U1 transpose plus U lambda 2 U2 U2 transpose
真没有厉害。
plus lambda n
然后还有一个
UN times UN transpose times F is equal to B equals B. Then this one is going to be lambda 1 U1 U1 transpose transpose times X 그쵸? times X plus lambda 2 U2 U2 transpose X plus lambda
我
n
死了。
UN
我
times
刚才
UN
不知道为啥麦突然
transpose times
开了，
X
然后你
is
在那
equal
儿
to
说 M2 行不行？
In other words,
不是我没我麦突
let's
然
say
开，我
here
上
is a
专业
matrix
课。
X, matrix A, S, then left hand side,
知道那是必
this
须的。
one, it's going to be the
管卖的。
现在
vector
我又退
of
出去
the orthogonal projection of
我麦
U1
突然开了，
U2
挂了网课。
and U3. The
Thanks,
sum of these
have
three
fun.
matrix, three vectors.
这没事儿，我没说什么。
In other words, if you consider some of the vectors, then you can find the approximate solution for the AX equals B. AX equals B. 자, 그래서 한국어로 설명하면 어떤 매트릭스 AX equals B가 A의 아이겐 스페이스가 이제 U1, U2, U3가 있을 때 X를 결국에 이 레프트 사이드를 풀어보면 X가 U1, U2, U3의 벡터들로 이렇게 프로젝션, 올수만 프로젝션한 벡터들의 합인 거죠. 그렇죠? 그렇게 표현될 수 있다. 그렇게 이제 이해할 수 있다라고 하는 거고, 이제 아까 뭐라고 했어요? 얘가 approximate solution이라고 했으니까 얘의 어떤 몇 개, 앞에 몇 개의 매트릭스 썸만 고려를 하면 우리가 approximate solution도 찾을 수가 있다. 라고 하는 게 이제 Spectral Decomposition을 사용하는 좋은 예시가 되겠습니다. 알겠죠? Okay, that's it. So any question? No? Okay, so this spectral decomposition is one of the popularly used one in computer science department. So please try to understand what the meaning is and what the meaning is and how to formulate this spectral decomposition. Okay? And the question is, 동인? 동현수 너무 좋은 질문이고 그 얘기는 우리가 다음 시간에 좀 얘기를 할게요. 그럼 어떤 아이겐밸류를 선택해야 중요한지. So the 동현수 question was about the order of the eigenvalues. 그렇죠? We will talk about this one in the next week. Next lectures. Okay? Any other question? No? Okay, so that's it. So we are almost done. So in this third day, we will finish this lecture to 13, lecture 13, and we will finish this semester. And we will take a final exam. I will let you know soon. I will announce soon. And our final exam will held in June 21. Offline exam, we will bring one page cheating sheet as done in midterm exam. 그렇죠? Yep. That's it. Question. 자, 한 번 더 설명. 우리 이제 거의 다 왔죠? 우리 다음 시간 목요일 날 이제 나머지 한 시간 끝내고요. 다음 한 주 지나고 그 다음 주 6월 21일 날 우리 이제 중간 아니죠? 기말고사로 여러분들과 만날 거고요. 그러고 나서 이제 이번 학기 마무리가 되겠습니다. 얼마 안 남았죠? 우리 조금만 더 힘을 내서 잘 마무리하고요. 오늘 배웠던 스펙트럴 디컴포지션. 사실 챕터 12부터 엄청나게 많은 theorem과 properties를 막 얘기하고 왔는데 결국에 요거 하려고 했던 거예요. 요거. 그만큼 중요하고 이게 너무나 많은 곳에 쓰이는 팩토라이제이션 기법이거든요. 그렇죠? 근데 요거까지 이제 우리가 오늘 얘기했는데 꼭 복습해서 이제 여러분들 걸로 만들고 우리는 이제 목요일 날 마지막 시간으로 여러분들과 만나도록 하겠습니다. 질문 없죠? Right. That's it. So this is end of today's lecture. Thank you very much and see you Thursday. 자, 여러분들 오늘 또 나 앞에 조금 테크니컬 프로블럼 있었는데 기다려줘서 너무 고맙고요. 꼭 복습 했으면 좋겠고 우리는 목요일 날 보도록 하겠습니다. 여러분 고생 많으셨습니다.